Dear students, in this paper, which is organic spectroscopy, we shall deal with the various aspects of spectroscopy. Spectral data, as you are aware, very important tools for chemists to identify and elucidate the structure of unknown organic compounds. They can be simple compounds and they can be very complex compounds which are found in biological systems. So, in this paper we shall begin first of all with the UV and IR spectroscopy, where we will do the correlation of UV bands with functional groups, how the effect of solvents, then the hydrogen bonding and base takes place on the electronic transitions. After the UV and IR spectroscopy, we shall discuss in detail the proton NMR spectroscopy or the 1H NMR spectroscopy. We shall talk about the natural abundance of 13C, 19F, 31P nuclei, the spinning nucleus, effect of external magnetic field, how the precessional motion and frequency vary, the energy transitions, chemical shift and its measurement, how it is done. We shall also study the factors which influence the chemical shift during the NMR spectroscopy measurement, the anisotropic effects, integrals of protons, how the spin-spin coupling, the splitting theory, how to calculate the magnitude of coupling constant, simple, virtual, complex spin-spin coupling, then chemical and magnetic equivalence, how to find out and what will be the impact on the NMR spectra. Further simplification of this complex NMR spectra, how it can be done with the solvent effect, field effect, double resonance and lanthanide shift reagents and also NOE technique. Then we shall try to apply all this knowledge, that is the application of proton NMR spectroscopy in the structural elucidation of simple and complex compounds. After understanding the proton NMR spectroscopy, we shall try to understand the 13C NMR spectroscopy. How the resolution and multiplicity of 13C NMR, 1S decoupling, noise decoupling, the broadband resonance, proton decoupling, and then based on this the structural application of the 13C NMR, and then we will also see how the DPT and the introduction to 2D NMR techniques, which will also further simplify and help us in making the structural elucidation. After the 13C NMR, we shall try to understand mass spectral techniques, that is the mass spectrometry. We shall discuss what is the theory behind the mass spectrometry, its instrumentation, what are the modifications done, how the molecular ions, the terms singly and doubly charged ions, what are the metastable peak, the base peak, isotropic mass peaks, relative intensity, FTMS, etc. How to recognize the M plus ion peak, general fragmentation rules, if you are given any structure, how the fragment will be occurring when you subject that particular compound to the mass spectra. And we shall discuss some various classes of organic molecules, including compounds containing oxygen, sulfur, nitrogen and halogens, and how the alpha, beta, allylic and benzylic cleavage happen. And we shall have a detailed discussion on the McLafferty rearrangement. And then after studying all these spectral techniques, that is UV, IR, 1H NMR, 13C NMR and mass spectroscopy, we shall try to solve some combined problems on UV, IR, NMR and mass. So, given a permutation combination of these spectral data, how you can identify what functional group is there, what type of carbon is there, how many type of equivalent hydrogens are there and so on. So, based on all this information, we will try to understand that how you can elucidate the structure of the given organic compound. And while solving these problems, to elucidate the structure or identify the functional group, etc., there should be some points kept in mind, and this will reiterate and you can try to understand what I want to say here when we go in further subsequent modules. In the UV visible spectroscopy, the types of bonds and electrons, they play important role in understanding the electronic transitions. The UV visible spectroscopy will give you information regarding the presence of conjugation, carbonyl group, etc., to name a few. Talking about the IR spectroscopy, the IR values from the IR spectral data will give you information regarding what functional group must be present in that particular molecule, based on obviously the reference values which we will study. The 1H NMR will tell us about the number and the environment of neighboring hydrogen atoms which are present. The 13C NMR will help you in getting the information about the type of different carbon atoms which are present in the molecule. And the mass spectral data will give you information about the total mass and fragmentation pattern of the molecule. And by combining all this information, we can easily find the structure of the molecule, whether it is simple or it is complex. But yes, we will begin with simple examples and slowly we will develop the how to find out the structure of complex molecules. So, with this background, let us begin the study of the first module. So, dear students, let us try to know the learning outcomes of this very first module of the paper, which is organic spectroscopy.
After studying this module, you shall be able to understand the electromagnetic radiation, analyze the electromagnetic spectrum, understand concept of UV visible spectroscopy, learn possible electronic transitions, and also know the working of UV visible spectrophotometer. Let us first learn what is an electromagnetic spectrum. The arrangement of all types of radiations in the order of increasing wavelength or decreasing frequencies is known as electromagnetic spectrum. The electromagnetic spectrum includes radio and TV waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. Radio waves have the longest wavelength, whereas gamma rays have the smallest wavelength and the highest energy of any radiation in the electromagnetic spectrum. Let us see why spectroscopy is important and what is it used for. Spectroscopy is the study of interaction of electromagnetic radiations with the matter under study. Molecules absorb energy in the form of electromagnetic radiation, which can bring different changes in molecule such as translational, rotational or vibrational motion, electronic transitions or ionization of the molecules, depending upon the wavelength or frequency of the electromagnetic radiation. The energy required for the transition from a state of low energy to a state of higher energy is exactly equal to the energy of electromagnetic radiation that causes transition. Now we will study what kinds of transitions are possible in UV visible spectroscopy. UV visible spectroscopy studies the electronic transitions between different electronic energy states within the molecules as they absorb light in the UV and visible regions of the electromagnetic spectrum. Since the absorption of ultraviolet or visible radiation leads to transition among electronic energy levels, it is also known as electronic spectroscopy. The ground state of an organic molecule contains valence electrons in three main types of molecular orbitals, namely sigma orbitals, pi orbitals, and non-bonding orbitals. Sigma bonding orbitals have lower energy than pi bonding orbitals, which in turn have lower energy than non-bonding orbitals. The two anti-bonding orbitals have higher energy are pi antibonding at higher than sigma antibonding orbital. Electronic transitions involve the promotion of an electron from one of the three ground states, sigma, pi or n, to one of the two excited states, sigma star or pi star. Before studying about the various electronic transitions, we will first learn about the formation of the bonding and anti-bonding molecular orbitals. In the diagram shown, two 1s atomic orbitals combine to give a sigma bonding molecular orbital, which is low in energy, and a sigma anti-bonding orbital, which is higher in energy. Sigma bonding orbitals and anti-bonding orbitals can also be formed between p orbitals as shown in the figure. The bonding molecular orbitals are obtained from the constructive or in-phase overlap between two nuclei. They have more electron density in the region between the two nuclei. The antibonding molecular orbitals are formed from the destructive or out-of-phase overlap of the two nuclei. They have minimal electron density between the two nuclei. In the formation of pi molecular orbitals, the two px atomic orbitals interact by parallel overlapping to form two pi molecular orbitals. One is pi bonding and the other is pi antibonding molecular orbital. Similarly, two py atomic orbitals interact by parallel overlapping to form two pi molecular orbitals. The energies of both the 2px and 2py atomic orbitals are the same. Therefore, the bonding and anti-bonding orbitals formed by them are also degenerate. In the pi bonding orbitals, electrons are found along the axis on which the nuclei of the atoms lie, whereas in pi antibonding orbitals, the electrons are found either above or below the axis. Now, we will study sigma to sigma star transitions. These are high-energy transitions shown by alkanes only. They are observed in the far UV region, which is less than 150 nanometers. Study of such transitions is usually done in a vacuum spectrophotometer. Since oxygen present in air absorbs strongly at 200 nanometers, pi to pi star transitions occur in compounds containing one or more unsaturated groups like simple alkenes, alkynes, aromatics, carbonyl, nitriles, nitro, etc. It is usually observed in the range 200 to 700 nanometer with high value of epsilon max. These transitions are sensitive to the substitution by another functional groups. This type of transitions occur in saturated compounds containing atoms with unshared electron pairs, that is non-bonding electrons. Energy required for these transitions is usually less than that required for sigma to sigma star transitions, and it gives rise to an absorption band at longer wavelength. The intensity of this transition is very low as it is a forbidden transition. Saturated carbonyl compounds show two types of transitions: low energy, that is N to pi star, and high energy, that is pi to pi star. Although transitions from N to pi star involve the lowest amount of energy, they are still found to be of very low intensity as this transition is symmetry forbidden. Thus, the most intense band for these compounds are always due to pi star transition. Some electronic transitions, which are otherwise theoretically possible, are generally not observed in UV visible spectroscopy. Therefore, there are some restrictions which govern the observable transitions. Transitions involving a change in the spin state of the molecule are forbidden. Transitions from the singlet to triplet or triplet to singlet are either not allowed or they are weakly observed. Let us now come to spectrophotometer and understand how it works. Spectrophotometer is an instrument which measures the absorbance of a sample as a function of wavelength. Absorption of radiation by a sample is measured at various wavelengths and plotted by a recording device to give the spectrum. The basic components of a spectrophotometer are a light source, sample area, and monochromator such as diffraction grating or a prism to separate the different wavelengths of the light, and a detector as is shown in this schematic diagram.
Having seen the schematic diagram of a spectrophotometer, let us see an animation which depicts the working of a UV visible spectrophotometer. A light beam is generated from a UV visible light source, which is then separated into its component wavelengths by a prism or a diffraction grating, which are the parts of a monochromator. The beam is then passed through a transparent cell containing the sample or the reference solution. After this, the intensities of the respective transmitted beams are compared over the wavelength range of the instrument. This instrument electronically subtracts the absorption of the pure solvent from the absorption of the solution and measures the absorbance or transmittance due to the compound itself. Finally, the instrument records a graph between the absorbance versus the corresponding wavelength.
Two types of dispersion devices, vis prisms and holographic gratings, are commonly used in UV visible spectrophotometers. In modern spectrophotometers, diffraction gratings are used as they are cheaper, easier to make, and give superior performance. The sample to be detected is placed inside the cell compartment of the spectrophotometer, and the monochromatic light is passed through the cell. The container which holds the sample solution is known as a cuvette. The most common cuvettes are typically rectangular in shape with an internal width of 1 centimeter and are usually made transparent material such as glass, plastic, as well as silica or quartz. Although glass cannot always be used as it absorbs light in the UV region, but it can be used satisfactorily in the visible region. The detectors used in a spectrophotometer are photodiodes, which operate on the principle of the internal photoelectric effect. The advantage of these detectors is their short response time, which allows real-time recording of spectra. The diagram shown depicts a UV visible absorption spectra. It usually shows the plot of absorbance against a broad range of wavelengths. A spectrum may have a number of absorption bands, as a molecule can have many functional groups associated with it. Different functionalities absorb radiation at different wavelengths. The wavelength of maximum absorbance is a characteristic value of a particular molecule, and it is designated as lambda max. There are two types of spectrophotometers. In a single beam spectrophotometer, only one beam of light passes through the sample. Therefore, it requires to take the reading for the reference and sample separately. In a double beam instrument, the light is split into two beams before it reaches the sample. One passes through a reference solution and the other passes through the sample. The reference beam intensity is taken as 0% absorbance, and the detector displays or measures the ratio of the intensities of the two beams. Double beam spectrophotometers operate faster and provide more reproducible results because they perform an automatic correction for the loss of light intensity as the beam passes through the sample and reference solution. Let us know what governs the absorption of radiation by a sample. It is Beer-Lambert law, which relates the absorbance and concentration of an absorbing substance. The fraction of incident light absorbed is directly proportional to the concentration of the absorbing substance and the length of the path of radiation through the sample. From the figure shown, it is clear that the fraction of incident light absorbed is independent of the intensity of the incident light, and each successive unit layer absorbs an equal fraction of light incident on it. For example, if 100 photons of light enter the first cell and only 50 photons come out from the other side of the cell. Thus the transmittance is 0.5 or 50%. If these 50 photons then pass through another identical cell of the same concentrations, only 25 photons will emerge, and so on.
Dear students, let us now summarize what we have learnt in this module. We have learned that spectroscopy is basically the study of interaction of electromagnetic radiation with the matter. The arrangement of all types of radiations in order of their increasing wavelengths or decreasing frequencies is known as the electromagnetic spectrum. And depending upon the frequency of the received electromagnetic radiation, the absorption of energy can bring about translational, electronic, rotational or vibrational motion and even ionization of these molecules. Although there are 6 possible transitions, that is sigma to sigma star, pi to sigma star, pi to pi star, pi to sigma star, n to pi star and n to sigma. But out of these, the most commonly observed transitions in the organic molecules are pi to pi star, n to sigma star and n to pi star. So, we will continue our study in the next module.